Several national, provincial, and local governments around the world have introduced policies to support the mass market adoption of plug-in electric vehicles. A variety of policies have been established to provide financial support to consumers and manufacturers, non-monetary incentives, subsidies for the deployment of charging infrastructure, electric vehicle charging stations in buildings, and long-term regulations with specific targets. Financial incentives for consumers are aiming to make electric car purchase price competitive with conventional cars due to the higher upfront cost of electric vehicles. Depending on battery size, there are one-time purchase incentives such as grants and tax credits, exemptions from import duties, exemptions from road tolls and congestion charges, and exemption of registration and annual fees. Among the non-monetary incentives, there are several perks such allowing plug-in vehicles access to bus lanes and high-occupancy vehicle lanes, free parking, and free charging. Some countries or cities that restrict private car ownership, for example, a purchase quota system for new vehicles, or have implemented permanent driving restrictions, for example, no drive days, have these schemes exclude electric vehicles to promote their adoption. Several countries, including England and India, are introducing regulations that require electric vehicle charging stations in certain buildings. Some governments have also established long-term regulatory signals with specific targets such as zero-emissions vehicle, ZEV, mandates, national or regional Code 2 emission regulations, stringent fuel economy standards, and the phase-out of internal combustion engine vehicle sales. For example, Norway set a national goal that by 2025 all new car sales should be ZEVs, battery electric or hydrogen. While these incentives aim to facilitate a quicker transition from internal combustion cars, they have been criticized by some economists for creating excess deadweight loss in the electric car market, which may partially counteract environmental gains. In the year of 2021, the total number of electric cars on the world's roads went to about 16.5 million. The sales of electric cars in the first quarter of 2022 went up to 2 million. China has the largest all-electric car fleet in use, with 2.58 million at the end of 2019, more than half, 53.9%, of the world's electric car stock. Tesla became the world's leading electric vehicle manufacturer in December 2019. Its Model S was the world's top-selling plug-in electric car in 2015 and 2016. Its Model 3 has been the world's best-selling plug-in electric car for 4 consecutive years, from 2018 to 2021, and the Model Y was the top-selling plug-in car in 2022. The Tesla Model 3 surpassed the Leaf in early 2020 to become the world's cumulative best-selling electric car. Tesla produced its 1 millionth electric car in March 2020, becoming the first auto manufacturer to do so, and in June 2021, the Model 3 became the first electric car to pass 1 million sales. Tesla has been listed as the world's top-selling plug-in electric car manufacturer, both as a brand and by Automotive Group for 4 years running, from 2018 to 2021. At the end of 2021, Tesla's global cumulative sales since 2012 totaled 2.3 million units, with 936,222 of those delivered in 2021. As of December 2021, the Renault, Nissan, Mitsubishi Alliance listed as one of the world's leading all-electric vehicle manufacturers, with global all-electric vehicle sales totaling over 1 million light-duty electric vehicles, including those manufactured by Mitsubishi Motors since 2009. Nissan leads global sales within the alliance, with 1 million cars and vans sold by July 2023, followed by the group Renault with more than 397,000 electric vehicles sold worldwide through December 2020, including its Twizy heavy quadricycle. Mitsubishi's only all-electric vehicle is the i-MiEV, with global sales of over 50,000 units by March 2015, accounting for all variants of the i-MiEV, including the 2 minicab versions sold in Japan. The Alliance's best-selling Nissan Leaf was the world's top-selling plug-in electric car in 2013 and 2014. Until early 2020, the Nissan Leaf was the world's all-time top-selling highway-legal electric car, and, as of July 2023, global sales totaled over 650,000 units since inception. Other leading electric vehicles manufacturers are BAIC Motor, with 480,000 units sold, SAIC Motor with 314,000 units, and Geely with 228,700, all cumulative sales in China as of December 2019, and Volkswagen. Electric road technologies which power and charge electric vehicles while driving were assessed in Sweden from 2013. 12 The assessment was scheduled to conclude in 2022. The first standard for electrical equipment on board a vehicle powered by a rail electric road system, ERS, Senelec Technical Standard 50717, has been approved in late 2022. Following standards, encompassing full interoperability and a unified and interoperable solution for ground-level power supply, are scheduled to be published by the end 2024, detailing complete specifications for communication and power supply through conductive rails embedded in the road. The first permanent electric road in Sweden is planned to be completed by 2026 on a section of the E20 route between Hallsberg and Örebro, followed by an expansion of further 3,000 kilometers of electric roads by 2045. A working group of the French Ministry of Ecology considers ground-level power supply technologies the most likely candidate for electric roads, and recommended adopting a European electric road standard formulated with Sweden, Germany, Italy, the Netherlands, Spain, Poland, and others. 166 France plans to invest 30 to 40 billion euro by 2035 in an electric road system spanning 8,800 kilometers that recharges electric cars, buses, and trucks while driving. 2 tenders for assessment of electric road technologies are expected to be announced by 2023. During peak load periods, when the cost of generation can be very high, electric vehicles with vehicle-to-grid capabilities could contribute energy to the grid. These vehicles can then be recharged during off-peak hours at cheaper rates while helping to absorb excess nighttime generation. The batteries in the vehicle serve as a distributed storage system to buffer power. As with all lithium-ion batteries, electric vehicle batteries may degrade over long periods of time, especially if they are frequently charged to 100%, however, this may take at least several years before being noticeable. A typical warranty is 8 years or 100,000 miles, 160,000 kilometers, but they usually last much longer, perhaps 15 to 20 years in the car and then more years in another use. Electric motors can provide high power-to-weight ratios. Batteries can be designed to supply the electrical current needed to support these motors. Electric motors have a flat torque curve down to 0 speed. For simplicity and reliability, most electric cars use fixed ratio gearboxes and have no clutch. Many electric cars have faster acceleration than average ICE cars, largely due to reduced drivetrain frictional losses and the more quickly available torque of an electric motor. However, NEVs may have a low acceleration due to their relatively weak motors. Electric vehicles can also use a motor in each wheel hub or next to the wheels. This is rare but claimed to be safer. Electric vehicles that lack an axle, differential, or transmission can have less drivetrain inertia. Some direct current motor-equipped drag racer EVs have simple 2-speed manual transmissions to improve top speed. The concept electric supercar Rimac Concept 1 claims it can go from 0 to 97 km per hour, 0 to 60 miles per hour, in 2.5 seconds. Tesla claims the upcoming Tesla Roadster will go 0 to 60 miles per hour, 0 to 97 kilometers per hour, in 1.9 seconds. Internal combustion engines have thermodynamic limits on efficiency, expressed as a fraction of energy used to propel the vehicle compared to energy produced by burning fuel. Gasoline engines effectively use only 15% of the fuel energy content to move the vehicle or to power accessories. Diesel engines can reach onboard efficiency of 20%. Electric vehicles convert over 77% of the electrical energy from the grid to power at the wheels. Electric motors are more efficient than internal combustion engines in converting stored energy into driving a vehicle. However, they are not equally efficient at all speeds. To allow for this, some cars with dual electric motors have one electric motor with a gear optimized for city speeds and the second electric motor with a gear optimized for highway speeds. The electronics select the motor that has the best efficiency for the current speed and acceleration. Regenerative braking, which is most common in electric vehicles, can recover as much as 1/5 of the energy normally lost during braking. Combustion-powered cars harness waste heat from the engine to provide cabin heating, but this option is not available in an electric vehicle. While heating can be provided with an electric resistance heater, higher efficiency and integral cooling can be obtained with a reversible heat pump, such as on the Nissan Leaf. PTC junction cooling is also attractive for its simplicity. This kind of system is used, for example, in the 2008 Tesla Roadster. To avoid using part of the battery's energy for heating and thus reducing the range, some models allow the cabin to be heated while the car is plugged in. For example, the Nissan Leaf, the Mitsubishi i-MiEV, Renault Zoe, and Tesla cars can be preheated while the vehicle is plugged in. Some electric cars, for example, the Citroën Berlingo Electric, use an auxiliary heating system, for example gasoline-fueled units manufactured by Webasto or Eberspacher, but sacrifice green and zero emissions credentials. Cabin cooling can be augmented with solar power external batteries and USB fans or coolers, or by automatically allowing outside air to flow through the car when parked. Two models of the 2010 Toyota Prius include this feature as an option. The safety issues of BEVs are largely dealt with by the international standard ISO 6469. This document is divided into 3 parts dealing with specific issues. Onboard electrical energy storage, i.e. the battery. Functional safety means and protection against failures. Protection of persons against electrical hazards. The weight of the batteries themselves usually makes an EV heavier than a comparable gasoline vehicle. In a collision, the occupants of a heavy vehicle will, on average, suffer fewer and less serious injuries than the occupants of a lighter vehicle. Therefore, the additional weight brings safety benefits to the occupant, while increasing harm to others. On average, an accident will cause about 50% more injuries to the occupants of a 2,000 pounds 900 kilograms vehicle than those in a 3,000 pounds 1,400 kilograms vehicle. Heavier cars are more dangerous to people outside the car if they hit a pedestrian or another vehicle. The battery in skateboard configuration lowers the center of gravity, increasing driving stability, lowering the risk of an accident through loss of control. If there is a separate motor near or in each wheel, this is claimed to be safer due to better handling. Like their ICE counterparts, electric vehicle batteries can catch fire after a crash or mechanical failure. Plug-in electric vehicle fire incidents have occurred, albeit fewer per distance traveled than ICE vehicles. Some cars' high-voltage systems are designed to shut down automatically in the event of an airbag deployment, and in case of failure firefighters may be trained for manual high-voltage system shutdown. Much more water may be required than for ICE car fires, and a thermal imaging camera is recommended to warn of possible reignition of battery fires. Most electric cars have similar driving controls to that of a car with a conventional automatic transmission. Even though the motor may be permanently connected to the wheels through a fixed ratio gear, and no parking pole may be present, the modes P and N are often still provided on the selector. In this case, the motor is disabled in N and an electrically actuated handbrake provides the P mode. In some cars, the motor will spin slowly to provide a small amount of creep in D, similar to a traditional automatic transmission car. When an internal combustion vehicle's accelerator is released, it may slow by engine braking, depending on the type of transmission and mode. EVs are usually equipped with regenerative braking that slows the vehicle and recharges the battery somewhat. Regenerative braking systems also decrease the use of the conventional brakes, similar to engine braking in an ICE vehicle, reducing brake wear and maintenance costs. Lithium-ion based batteries are often used for their high power and energy density. Batteries with different chemical compositions are becoming more widely used, such as lithium iron phosphate, which is not dependent on nickel and cobalt, so can be used to make cheaper batteries and thus cheaper cars. The range of an electric car depends on the number and type of batteries used, and, as with all vehicles, the aerodynamics, weight and type of vehicle, performance requirements, and the weather. Cars marketed for mainly city use are often manufactured with a short-range battery to keep them small and light. Most electric cars are fitted with a display of the expected range. This may take into account how the vehicle is being used and what the battery is powering. However, since factors can vary over the route, the estimate can vary from the actual range. The display allows the driver to make informed choices about driving speed and whether to stop at a charging point en route. Some roadside assistance organizations offer charge trucks to recharge electric cars in case of emergency. Most electric cars use a wired connection to supply electricity for recharging. Electric vehicle charging plugs are not universal throughout the world. However, vehicles using one type of plug are generally able to charge at other types of charging stations through the use of plug adapters. The Type 2 connector is the most common type of plug, but different versions are used in China and Europe. The Type 1, also called SAEJ 1772, connector is common in North America but rare elsewhere, as it does not support three-phase charging. Wireless charging, either for stationary cars or as an electric road, is less common as of 2021, but is used in some cities for taxis. Electric cars are usually charged overnight from a home charging station, sometimes known as a charging point, wallbox charger, or simply a charger, in a garage or on the outside of a house. As of 2021, typical home chargers are 7 kilowatts, but not all include smart charging. Compared to fossil fuel vehicles, the need for charging using public infrastructure is diminished because of the opportunities for home charging. Vehicles can be plugged in and begin each day with a full charge. Charging from a standard outlet is also possible but very slow. Public charging stations are almost always faster than home chargers, with many supplying direct current to avoid the bottleneck of going through the car's AC to DC converter, as of 2021 the fastest being 350 kilowatts. Combined Charging System, CCS, is the most widespread charging standard, whereas the GB/T27930 standard is used in China, and CH8MO in Japan. The United States has no de facto standard, with a mix of CCS, Tesla superchargers, and CH8MO charging stations. Charging an electric vehicle using public charging stations takes longer than refueling a fossil fuel vehicle. The speed at which a vehicle can recharge depends on the charging station's charging speed and the vehicle's own capacity to receive a charge. As of 2021, some cars are 400 volt and some 800 volt. Connecting a vehicle that can accommodate very fast charging to a charging station with a very high rate of charge can refill the vehicle's battery to 80% in 15 minutes. Vehicles and charging stations with slower charging speeds may take as long as 2 hours to refill a battery to 80%. As with a mobile phone, the final 20% takes longer because the system slows down to fill the battery safely and avoid damaging it. Some companies are building battery swapping stations, to substantially reduce the effective time to recharge. Some electric cars, for example, the BMW i3, have an optional gasoline range extender. The system is intended as an emergency backup to extend range to the next recharging location, and not for long-distance travel. Thank you for watching this video.